Hey, good afternoon, everyone. Welcome to our Beyond the Scope seminar series. I'm glad you guys could make it this afternoon for our talk. We're going to be having the talk today by Stephen Buna. He'll be talking about energy dispersive X-ray spectroscopy in the SEM. Let's switch slide, Steve. So Steve's going to give a quick overview of X-ray, dispersive X-ray spectroscopy with a couple examples and everything. And just as a reminder to everyone about what this series is all about is to ask lots of questions. So there's a couple different ways to do this during the webinar. Definitely put things into chat if you want a quick answer about it. I'll try and answer some stuff in there if I'm able to, or Steve can get at the end. If you want to ask questions, the easiest way to do it is ask the Q&A, and it's easy for us to see those at the very end. And if you have in-depth questions, we're around to chat afterwards, and we can discuss things online that way, or you can email us afterwards. And then also, if you have any difficulties, again, just put it in chat, and either myself or Ashley will get to you. So let's go ahead with Steve's talk.
Okay, thank you, Dan, for the introduction. As Dan mentioned, my name is Steve Buna, and today we'll be discussing some SEM-EDS examples and asking kind of this general question of how did that get there, and we'll explain why I arrived at that name for the title. So as you've seen throughout this series, CEMAS is closed right now, but we are still providing support for our users remotely through these weekly webinars, as well as through one-on-one consultations. So if you have questions about data you have already collected, or if you have questions about experiments you want to plan for the future, please feel free to reach out to one of the instrument managers for the appropriate instrument, and we can work with you to discuss those questions you might have. We also have some capabilities set up for remote analysis of data that you have already collected. If you're not set up with that capability yet, please let us know by contacting that email address, and we can get you access to those resources. So CMS, at our facility, we are fortunate to have quite an extensive suite of characterization tools, a variety of different types of transmission electron microscopes, some dual beam instruments, and then our 4 scanning electron microscopes, as well as some other analytical techniques like our HeliScan X-ray micro CT, our X-ray diffractometers. And all of these different techniques are going to be featured in some way during the course of this webinar series. So if you check the schedule and you missed one that you wanted to see, let us know, because we have them recorded so that you can look at them later on your own time. And for today, we are specifically looking at the technique energy dispersive X-ray spectroscopy as it applies to scanning electron microscopes, although it can also be used in transmission microscopes. There are just a few caveats that distinguish how you collect and analyze the data. But primarily what we'll be discussing is as it relates to these types of instruments. So to give you a little bit of background about me, I grew up in the far northwest suburbs of Chicago, Illinois, so not very far away from where that dot is on the map. I stayed close to home for school. I went to Northern Illinois University for my bachelor's and master's degrees in applied physics. After doing that, I moved up to East Lansing, Michigan for a few years to get my PhD in materials science and engineering at Michigan State. And then in 2013, I came straight to Ohio State to take a postdoc position working with Joseph Harrimans in mechanical engineering and with the Center for Emergent Materials for a few years. And around that time, I was able to find an opening at CMS for a staff position specializing in scanning electron microscopes. And so I've been working at CMS since 2017. And on a personal note, if you look at these 3 institutions, if you know much about college football, then you may appreciate the fact that for my time as a student and employee, there's been a pretty good run of seasons. I think over the last 10 years, there may have been a total of 3 or 4 losing seasons between those 3 schools. So it's been a good time for me in college football Saturdays, but that's not what we're here to talk about today. We are here to discuss this question of how did that get there? So I chose this question to use in the title because I think it does a good job of embodying the sentiment that I tend to encounter when I work with users to help them with their EDS data collection and analysis. The really nice thing about modern equipment and software is that it makes it very easy to collect EDS data. The bad thing about modern equipment and software is that it makes it very easy to collect EDS data. And so a lot of the details are sort of hidden inside of the algorithms, and it's easy to overlook some things that may cause problems with the way the data are interpreted. So as a researcher, this is where you really have to distinguish yourself and earn your money by being at least a little bit smarter than the technology you're using to conduct your research. So I have to add a disclaimer here that this is an extremely broad topic. We do not have nearly enough time today to get into all of the different nooks and crannies that we could talk about in terms of the theory and background. I'm going to try to move quickly to get through everything, but we're going to mainly try to emphasize some specific examples of situations where adjustments to the parameters will dramatically improve the collection and analysis process of the data. I think it's important, though, to start with some basic descriptors to make sure that we're all on the same page talking about this technique. And we can ask just the very straightforward question of what is EDX or EDS? If you have seen this acronym before, you may have also seen the XEDS. There are different varieties of it. But in all cases, it's talking about the same thing, that is energy dispersive X-ray spectroscopy. And to be specific, this is electron induced. So you can do this type of analysis as well with X-ray excitation instead of electrons. But in these cases, we are describing specifically using an electron beam to excite these X-rays. And I think it's helpful to go through this acronym backwards to understand what we're actually doing here. So this is a spectroscopic technique, which means we are looking at the measurement of interactions between radiation and matter. And in particular, we're talking about X-rays. So these are relatively high energy photons, and we're looking at the energy dependence of those X-rays. So there are other types of spectroscopic techniques you may be more familiar with that talk about wavelengths or inverse wavelengths. But in this case, we are looking at the energy specifically of X-rays that are generated by materials after being exposed to an electron beam. We'll go quickly through this basic idea of how this process works. So if you've done this before, you probably have already some sense for how this plays out. But in a scanning electron microscope, we have our sample, and then the beam comes down from the top, hits the sample, and generates a wide variety of signals, both electron signals and photon signals. For today, we care primarily about these characteristic X-rays that come out of the material. What makes them characteristic is that they are essentially atomic fingerprints, if you will, in the sense that the energy of these X-rays is very specific and is determined by the difference in energy between electron levels around the nucleus of the atoms inside of the material. And so if we know the energy of these X-rays, we can work backwards to figure out what element produced them. And that allows us to do some of these different types of composition analyses. After the beam hits the sample and generates all these X-rays, you have a detector inside of the chamber somewhere, and the X-rays are collected and then sorted, and you get these histograms where you see different intensities at different energies, which correspond with elements that generated the X-ray at that specific transition. And so this is our EDS spectrum, and this is what we do a lot of our analysis on. So I already kind of gave away the answer to this one, that EDS gives us information about composition, so we can use this for both qualitative and quantitative analysis to figure out which elements are in the sample, where they are in the sample, and about how much of each element we have. I'll emphasize at the beginning here that qualitative analysis is typically going to be much easier to do. The requirements on the sample and the parameters in order to get useful qualitative information are much less stringent than what they are if you want to get precise quantitative information. So you don't necessarily need to do as much work to get information about which elements and where, but if you want to know how much, then you're going to have to put a little bit more work into your analysis. So we have a little bit of background. Now we can imagine a typical scenario, right? You have material you're working on and you have some questions about the composition of that material. So you take it to CMS or whatever your local microscope facility happens to be, and you do some SEM analysis on the material. You collect your spectrum like we talked about on the previous slides. The software that runs that collection process will give you answers to your questions. It'll tell you which elements, where they are, and about how much you have. So that process is done. You have answers to your questions. So you take that information, you put it in your dissertation, you graduate, you publish papers, you get grants, and you win Nobel Prizes. So everything is great. It all sounds very easy, and it is pretty easy. So why would that possibly not be as straightforward as it seems? And unfortunately, there's lots of things that can go wrong in that process. So we don't want you to have to retract your papers or to return your Nobel Prizes. So when you get to this step, it's important to put on your critical thinking cap for a minute and think about some of the ways that your results might not be as straightforward as you were hoping they would. So we can run through some situations where the data you collect may not be useful. In particular, rough surfaces can be problematic. This example shows an especially large feature on the surface, which is actually blocking X-rays from this region and preventing them from reaching the X-ray detector. So when you look at the phase map, you don't even have any signal really from this part of the sample, although we know or can infer from this backscatter image that it's likely the same type of material, but we cannot say really anything about it because of how rough the surface is. If you have especially small features, then there may not be enough volume of material to generate X-rays to be able to figure out what those things are. It also is not uncommon to see samples that are dirty or contaminated, where you're picking up X-rays from parts of the area that are not actually your sample. And drift of samples during data collection is also not an uncommon problem, where EDS data collection is a process that involves acquisition times that are hundreds or thousands of times longer than what you'll normally encounter with imaging. So even materials that normally can handle the electron beam well under typical imaging conditions will sometimes be prone to drifting during data collection with EDS. So drift correction algorithms can help with that, but they do have their limits. The acquisition settings can sometimes cause problems if, for example, your beam energy is too high or it's too low. In a SEM, we span the full range of energies that most characteristic X-rays are in. So you can have situations where you can be too high, and you can also have situations where you can be too low. Part of that can also mean that if you don't collect enough data, then your spectrum peaks may not be big enough or well-defined, and the algorithms cannot fit them correctly. So you're not able to determine which elements are present or how much you have. You can also have issues where your detector settings are not optimized so that the dead time is too high or too low, and you'll start to see your peak shapes will change, or you'll get more intense artifacts in the signal spectrum. You can also have situations where, depending on how you set up the microscope, there may be lots of spurious X-rays, meaning signals coming to hit the X-ray detector that are not actually coming from your sample. So these can be problems. You can also run into issues with the analysis itself if you end up with a spectrum where the peaks are not identified correctly or not all the peaks are accounted for. If you go into your analysis thinking you know exactly what should be in your sample and then you cut out certain elements, then they may be present, but you're not accounting for them, so your analysis is going to be flawed. Okay, so to really understand for the examples that we're going to get to next why some of these things are problems, I think we need to also focus a little bit on specifically with the spectrum what can happen. If you've been trained by me at CMS to do this type of analysis, you've probably heard me say before that EDS tends to tell you more about your sample than you actually wanted to know. And part of the reason for that is that X-rays can come from a wide variety of sources during your experiments. So similar to what we were just talking about on the previous slide, the sample can generate a lot of X-rays from different sources, in the sense that what we really care about, the whole reason you do EDS analysis, is because we want to get this signal, the characteristic X-rays from the features that we're interested in. That's really what we're trying to extract from all of this and why we are collecting data. But the spectrum is also going to contain X-rays from other sources. So other parts of the sample, you'll have backscattered electrons running around inside the material. They're also going to generate X-rays, and anything else that's present in the image area has a chance to contribute to your spectrum. So if you're mounting your sample in epoxy or resin, you can see contributions from that. Polishing media, this is not uncommon to see silica or alumina or diamond left behind on surfaces after polishing. That shows up in your EDS data. And then conductive coatings. So if you're looking at materials that are not normally electrically conductive and you want to perform EDS analysis, you can, and one way to do that is to coat the material with something that does conduct, like carbon or metals. The problem is that not only will the incoming beam be attenuated slightly, but you'll also get some of those X-rays to show up in your spectrum, and that can cause some problems. The microscope system itself can also contribute X-rays. So the sample holder, the stage that the sample is on, and the chamber walls, you can potentially get X-rays from those places. And the detector itself can cause problems if you have artifacts. Two that are especially well-known and common are what are called sun peaks, where two X-rays are counted essentially as one because of the timing between when they hit the detector. And then escape peaks as well, where essentially you have a peak located just slightly away from the characteristic peak you're looking for, but differentiated by the fact that it was absorbed and then re-emitted. So those are all different reasons why you may have some issues with the peaks that you're looking at in your spectrum. Okay, so with that said, I think now we're all on the same page and we can move on to talking about some of these examples that I've pulled. The situations that I'm about to describe are all based on real materials, real events, things that I've seen and come across at CMS. The names have been changed to protect the innocent, especially since some of these examples come from my own projects. So if you're savvy, you might be able to figure out which are which, but if not and you're curious, just let me know afterwards. I can tell you either way. Starting with contaminated samples, I've seen this happen multiple times where if you are working in a lab space where you share sample prep equipment, it's going to be possible that you'll find in your sample elements that you shouldn't find, but that are present in your colleagues' samples. So if you're sharing a furnace or crucibles or ampules, cross-contamination can happen. So definitely caution you to be extra careful with that. Similarly, if you work on materials that you prepare in solution, so you work with buffers or solvents, it's not necessarily uncommon to see leftover salts or other things that are present after the material has been dried. Okay, so we talked a lot about how X-rays can come from lots of other places besides your sample, but in these cases, they would be real signals actually coming from the sample itself, but not where they're supposed to be in terms of the sample composition. So sometimes it's a real signal and you have to be aware of that possibility. Low vacuum is an interesting case for EDS analysis because I mentioned that you can coat materials to make them conducting if you want to do analysis. The other option, if you don't want to have to coat the material, is to do the analysis under low vacuum conditions. This works. It can be done. You can get useful information. This is a situation, though, where you are much more likely to get qualitative information than quantitative results. So to kind of go through an example here, this is the bite surface of a human tooth, a backscattered image collected under low vacuum conditions. So in this case, we didn't want to have to coat the material with anything to alter the native surface. So doing this analysis under low vacuum, there's a paper from Dale Newberry at NIST. The guys there, obviously this is what they do. They have a lot of really good research into how to do your analysis with better accuracy. So if you're looking for resources, Dale Newberry and Nick Ritchie at NIST have published extensively on a lot of these topics. I would highly recommend just looking for whatever they've published and digging through that. But this is a particular paper from 2002 where he describes some of the issues that come up with low vacuum EDS analysis. And so part of the problem is that what you expect to happen under high vacuum is for the beam to follow the dark line here and have a well-defined spot that it hits on the sample surface with an intensity distribution that roughly corresponds with this Gaussian shape. The problem is that when you have a lot of vapor inside of the chamber, as you do with low vacuum operation, the beam is going to undergo a lot of elastic scattering, meaning that an electron that was supposed to hit the sample here is going to get deflected somewhere and then end up hitting a sample over here. And so the software thinks that the beam is here, and it's correlating that with an X-ray that was detected after being generated actually somewhere over here. And so that area is described by this term they call a skirt. And so depending on the parameters you use for your data collection, this can be potentially the size of millimeters away. So that is outside the field of view of the sample in this image. So what that means is that if you do your data collection and analysis, you can see things that kind of surprise you and don't really seem like they make sense, depending on how carefully you scrutinize the results. So in this case, this is a bite surface. We know there's some topography here. And when you just look at this overlay of all the different elements identified automatically in the spectrum, these are real peaks. So there is really a peak for nickel and aluminum and titanium and iron and zinc. And so if you don't know better, you might think, oh, that's just a weird crown or something that's on the tooth, even though you might expect there to be some difference in the backscatter image. But this whole area seems as though it contains predominantly nickel. And so until you think more carefully about what's happening inside the microscope, and you realize that actually what's probably happening is you're getting this process and you're seeing X-rays generated by the stage, not actually by the sample. So you have to be a little bit careful if you're doing EDS analysis. Even qualitative analysis in low vacuum can cause some issues like this to come up. So you can mitigate this a little bit, at least by adding a pull piece extension onto the microscope. And what this will do is shorten the path length of the beam through the gas, and then reduce the size of this skirt and give you much more localized information. The problem with that is it significantly reduces the field of view. And so instead of being able to look at an image area like this is about the diameter of the pull piece attachment. But you get much more reliable results out of it. So there's a big trade-off to be made, but you can decide for yourself what is appropriate for your samples. And if you need some help, I'd be happy to assist you with that. To drive this point home, here's another spot where low vacuum EDS shows in the backscattered image, we have some features of different grayscale intensity. This oxygen map makes sense. There's features that correlate with what you see here. So this is useful qualitative information, but you don't really need a PhD in material science to realize that one of these things is not like the others. And so if you see something like this pop up in your results, that should set off some red flags that this doesn't really seem to correlate with anything in the sample. So I should be suspicious that the nickel signals is actually just an artifact. Okay, overlapping peaks. This is another very common way that you can get some errors in your analysis of your data. So I mentioned early on that the X-rays that are generated, these characteristic X-rays, are fingerprints of the elements, and that is true in the sense that the way, the location of these peaks on the spectrum is very specific to the element, but because there are multiple types of transitions that can happen, sometimes you get coincidences where different elements will have different types of transitions that are all close together in energy. And in this case, these are 3 transitions very close to about 1.7 keV. So if you rely on automated peak ID, especially if the software is only looking for 1 peak per element, then this can be an issue that pops up. And as an example, again, calling on Dale Newberry here, we see, in this case, this is a calcium fluoride sample, very well defined. There are only 2 elements plus some carbon on the surface, yet the EDS software tells him that there's yttrium present because there's a calcium escape peak that corresponds exactly with the location of this yttrium L edge. So he knows better that there isn't actually yttrium in the sample, but if he didn't think about it and just trusted the results, then he would have included this. The giveaway sometimes is that this would show up everywhere you would see calcium, and vice versa. There would be no places in the sample that would have yttrium without calcium and calcium without yttrium, because these two are actually essentially the same peak, but just differentiated by that artifact process. So Dale Newberry was kind enough to put together this table in his paper for all of us to use. So really, you can find a transition below 5 kV for pretty much every element in the periodic table. So that means it's possible to do EDS analysis at low voltages of 5 to 10 kV. But when you do that, you can see that it starts to get pretty crowded down here. And so these are commonly confused or very similar transitions that you should be aware of. And you can do the math yourself to look for artifacts. So for example, the oxygen peak here, if you have an oxygen sum peak, that's pretty much exactly in the same spot as the sodium peak. So it's not limited to just characteristic X-rays. The artifacts can also pop up at different points. So that can be an issue with the automated element ID. So to show you an example of this, here we have a stained tissue sample with heavy metals in it, where the software is looking for osmium L peak, which is all the way out here, and it sees it and gives you this nice picture. Unfortunately, though, there's also a overlap between the osmium M and the yttrium L at about 1.9. They're only separated by about 17 electron volts. So that's pretty much impossible for most EDS detectors to differentiate. And in that case, if it's looking for yttrium, as we saw in the previous one, it's going to label yttrium, even though it's not present. There is no yttrium in the material, but it's going to identify both automatically unless you go in and tell it to ignore that one. So be aware of overlapping peaks. I think we have a PowerPoint issue. Bear with me. Software is frozen. Okay, so one thing I wanted to talk about that is starting to come up more often is that people are coming in to use the SEMs and looking at semi-transparent samples. And so if you're doing STEM imaging or TKD experiments, you may also want to then go and collect composition information about your sample. You can do this, it'll work. The problem is that when you go to voltages that are typical for EDS collection, you end up having transmission through the sample. And so when that occurs, you can no longer apply all of the assumptions you would use for analyzing bulk samples. And instead, you have to essentially treat the material as if it's a TEM foil being analyzed at low voltage. So now you have to deal with all the problems that come up with TEM samples. And part of that means changing the quantification model away from whatever is used for your bulk materials and switching it to what would be used for a transparent material, and then having some information about the thickness and density, and then also realizing you're now more likely to see X-rays from the chamber since the beam is actually penetrating through your material. I will be presenting on this on whatever version of an M&M meeting we have this year. So if you'd like more information, let me know and we can discuss that in more detail. Okay, so I have some considerations I want to get to at the end, but I wanted to go through an important example first to invert this question and kind of approach this topic from a slightly different angle and ask, what did we miss? So it's not necessarily uncommon to come across a situation where some material that's produced is found to contain contamination, and there's a hunt begins to figure out where the contamination comes from, right? So in this case, for this particular example, These are metallic terbium shavings that were used as part of a precursor to grow some films, and inside of those films, it was found that there was some fluorine contamination. So in a effort to track down where that was coming into the samples, SEM-EDS was selected as one of the techniques to try and search for the origin. So to do this, started with a fairly low magnification element map to look for hints of a fluorine concentration. So in this case, we're doing the opposite. You don't necessarily know where the element is concentrated. And if you look at the spectrum from this whole area, if there is any fluorine present, it's going to be such a small amount you probably wouldn't see it, and the auto ID wouldn't find it. But you can add it yourself and then look at the element map and see if any spots light up, since each pixel has its own spectrum. So in this case, there was a spot that looked like maybe there was some extra intensity. So you can zoom in on that. And when you look more closely at that surface, you see there are some features that appear to have maybe a little bit more fluorine than they should. And then again, zooming in, you find that there are sort of these 5-micron bubbles on the surface that do indeed show a fluorine peak in their spectrum. And so now you can track down the origin and say that the contamination comes from the precursor material and not from some other step in the film growth process. Okay, so last set of technical information here. These are other considerations that I wanted to mention because they have all come up specifically through interactions I've had with people at CEMAS. And while I have your attention, I feel like it's a good opportunity to share some of these tips. If you're working with samples that contain a lot of carbon and you want to do EDS analysis, it's not a bad idea to not use carbon to mount them. Instead, try to put them on copper tape or something else that will give you better contrast. It's also a good idea if you're doing low magnification analysis to make sure that the beam is centered so that you get uniform illumination of the image area before you collect your data. It's also, we've talked about selecting your accelerating voltage. In general, you want to be balancing the over voltage and the X-ray volume. I didn't really talk about these, one of the background topics that we skipped, but especially in situations like this, I see a lot of people with these kinds of samples where you have intermetallic phases or precipitates that form, and you want to do some composition analysis of these features. Well, you can see right away in the backscatter image here that they're kind of fuzzy on the edges, which tells us that at this voltage, we are seeing some penetration through the surface, and that's going to affect the area of the material that we're getting our X-rays from as well, which means that if you really want to determine the composition of these two things, you need to make sure that you're only getting X-rays from one or only from the other. So be extra careful if you're dealing with small precipitates and similar. These are quite small, actually. So if you need help with this, let me know. We can talk about it separately. Adjusting your over voltage will have consequences, systematic consequences for your quantification results. So Brian Welk was kind enough to share with me some of the data that he's been collecting where you get slightly different results. It's not necessarily a huge difference, but it can be on the order of 0.5% absolute value from quantification, even of a homogeneous material. So what that means is if you are in a position where you have to know the exact composition to a high level of accuracy and precision, then this is probably not the right technique that you want to use. If you are in that position, let me know, and I can recommend some different methods depending on the types of materials you're working with. Something that I don't think people consider often is the channel limit. So this has also come up a few times where there's this setting you can choose in most the software packages where you pick either 5 EV per channel or 10 EV per channel. And it's not necessarily that's something that's obvious what that means, but it's important because essentially this is the number of histogram bins that you're putting into your spectrum. So on the ones we use at CMS, we have about a 4,000 channel limit, which means that if you run your data at 5 EV per channel, then you can collect data at a 20 kV beam energy and have no problems. But if you go above 20 kV, your spectrum is going to cut off at 20, and unless you switch to 10 EV per channel, and then you're going to have issues with background fitting and your analysis will be problematic. So just be aware of this if you do work at higher accelerating voltages. Typically, to avoid running into problems where there's not enough signal to get good quantification results, it's good to get as much data as you can. There is a point of diminishing returns in that it's not always worth it to run the collection forever, but insufficient counts can be a big problem, especially for minor constituent elements in your material. So up the current if you can, and then just make sure you pay attention to the dead time. I very recently learned that if you do line scans for quantification, it's a good idea to make sure they repeat. I can show you how to set that up. Otherwise, a single pass is probably not going to give you enough counts to get accurate information. It's good to double check the results of a line scan against point spectra. And if they don't agree, then I would trust the point spectra more. Okay, so after all of that, we asked our questions, how did that get there? And then we inverted it to ask, what did we miss? And I think the goal should be to ask yourself, what can we say with confidence when you're doing this type of analysis? This is always a good bottom line question to ask because whether you're trying to look for elements or eliminate the possibility that elements are present, you should always be careful and take a conservative approach to interpreting your data. So with that, I will conclude. And here is the schedule for the next month of talks in this series. And then if you are interested in reaching out to us outside of this webinar series, please feel free to connect through any of these different routes.